Hello and welcome back. In our last video, we were discussing the programmable interrupt timer. And in this video, I'm going to take you through communication protocols and in specific the 8251 UART. First of all, what are communication protocols? Let's take a common example. So whenever you lift the phone, what is the first thing you say? You'd say hello. And you expect a hello from the other side. This is a protocol, and a protocol accepted by human beings. Similarly, when two pieces of electronics talk to each other, there is a standard protocol that is expected. The protocol can broadly be categorized as hardware parts of the protocol and the software parts of the protocol. Under hardware, you have the pin-out diagrams, which pin will be the transmit pin, which pin is the receive pin, so on. So these are all defined by standards. You have voltage levels that are defined by standards. Should it be plus minus 3 volts, plus minus 5 volts, plus minus 12 volts? Different types of protocols have different standards for them. What is the maximum distance over which you can transmit data? So for example, if you take your television remote control, can you control the TV from the next room? No. Do you need line of sight? Yes. Can you do up to 10 meters? Maybe. So these are kinds of standards that the protocol defines. Should it be simplex, duplex or half duplex? What is simplex? Either you transmit or you receive. Right? So a remote control is a transmitter only and the television is a receiver only. Simplex protocols. A duplex is both transmit and receive. And a half duplex is transmit or receive at any point in time. What about synchronous or asynchronous? We'll discuss that a little detail, but those are also standards that are defined in communication protocols. These are the hardware parts of the protocol. On the software side, you talk about the syntax. Should there be a start bit? If so, is it a high or a low? Should there be a stop bit? If so, should it be a high or a low? What is the duration of the start bit and the stop bit? What about error detection and correction protocols? They're called ECC protocols. What are they as defined by the standards? What about the number of bits that can be transmitted per chunk of information? Again, a software protocol. In terms of semantics, so one is the syntax, the other is the semantics. In terms of semantics, what does the meaning of each section of the data that gets transmitted? The sequence of bytes. Is it low byte first or the high byte first? What about the information protocol? What should the header contain? What should the tail contain? What should be the information, design of the information in between, so on and so forth. These are typically protocols in any communication standards. If you look beyond that, so what we are really talking about is how should the bits be sent across when you're communicating between two devices. In this example, what you've really got is the way the bits would appear at the receiving end. So you start with a start bit, typically in this case an active low signal, so it's at 0. Then you have the actual data bits that come in. And then finally you end it with a parity bit, which tells you whether it's odd parity or even parity, followed by a stop bit. So this is an example of a software protocol which is used in many communication standards. What about asynchronous digital communication? Now in this example, you would see that the transmit of device 1 is connected to the receive of device 2. The receive of device 1 is connected to the transmit of device 2. So this is a duplex protocol. There is also a common ground signal that connects the two devices, because when the signals get transmitted back and forth without a common ground, it is normally treated as noise. So one bit at a time is sent from the device 1 to device 2, from the transmit pin to the receive pin. So if you're going to transmit 8 bits, it has to be sent one bit after the other 8 times. There is no separate synchronization signal in this. That's why it's called the asynchronous protocol. The synchronization signal must be enabled by the quality of the data that gets sent and the format of the data that gets sent across this transmission line. And it is the responsibility of the receiving side, which in this case is device 2, to ensure integrity of the data received. And in case there is a doubt, it must flag an error to the device 1. This integrity can be established by error correction codes, error detection codes, and as simple as by a parity code. Important thing, in an asynchronous digital serial transmission, the two sides do not negotiate with each other as the transmission is going on, and this can sometimes lead to erroneous data being transmitted back and forth. In the case of synchronous, the primary difference is that an additional line it really connects the two devices together, and this line carries a clock signal, and this helps to synchronize data back and forth between the two devices. What about the correction protocol, or in the case of synchronous digital device, how is synchronicity maintained? How is the device that receives information synchronous with the device that transmits? I said that there is a clock signal. And of course, a clock signal helps significantly in synchronizing data transmission. But a clock signal is not perfect. A clock signal can have skews, can have delays, so on and so forth. And in that case, you also tend to transmit what are called synchronous bits of information that helps the receiver understand when a data is about to be transmitted, when the data is about to be concluded, so on and so forth. This significantly enhances the accuracy of information transmitted between the receiver and the transmitter. These asynchronous devices or synchronous bits of information is part of the software protocol for synchronous serial digital communication. This sometimes is of course used during asynchronous serial digital communication as well, because in those cases there is no clock signal also to fall back on. What about the basics of a parallel? So we've spoken about serial digital communication. There is therefore something called a parallel digital communication as well. In the parallel digital communication world, it's just not one signal that goes from a transmit pin to a receive pin. There are 8 parallel lines, which means 8 different pieces of wire that communicate across the two devices. This obviously makes communication much more costly, and I mean, just because you now have a cable that has 8 pieces of wire running through them, you also have typically a clock signal that also runs through this, and of course the common ground. So what happens in this case is really that it is faster, right? So because you've got 8 parallel bits of data coming back and forth, it is much faster. It is not one after the other. It is all 8 in synchronicity. But what happens really is that the hardware becomes more complex, more wiring is required, and it can lead to a different kind of error. Every cable, every wire that connects the transmitter and the receiver has its own transmission delay. And in the world of microprocessors, these delays can be significant, because even though the delay can be a few micro or nanoseconds, when high-speed microprocessors are connecting to each other, these time delays lead to what is called skewing. And it is therefore important, even in the case of parallel bus transmission, to talk about data synchronization, to have synchronization bits that communicate the start of the information transmission. You may have start bits, you would have stop bits, you would have error correction codes, so on and so forth. And all of this together adds to the complexity of transmission across a parallel bus. And yet, just by the sheer fact that a parallel bus is so much more faster, at least 8 times faster than a serial transmission bus, many applications require them. There are 2 kinds of standards that I'm going to help you understand. One is called the RS-232, that's a serial standard. And in this standard, the software protocol is really up to the user to define. In terms of the hardware protocol, it is asynchronous between two devices, so there's no clock signal. It has a voltage that can vary from plus or minus 3 volts all the way up to plus or minus 15 volts. So plus 3 to plus 15 is considered as high, minus 3 to minus 15 is considered as low. Data signals and control signals use opposite polarity. So the data is, if the data signal is positive, then the control signals are negative, and vice versa. And pinouts are completely defined. There are 2 kinds of connectors. There is a 9-pin connector and a 25-pin connector. In both cases, the pinouts are defined by this protocol. The RS-232 is the most common protocol used in normal computer applications. It's also called the COM port. So you have COM1, COM2, COM3 ports that are present in typically most desktops and in many cases many laptops. The other kind of standard communication is the general purpose interface bus. It's called GPIB. It's an IEEE standard as well. Here too, the software protocol is left to the user. The hardware protocol is defined by the standard, and this is an asynchronous protocol, but it can connect many devices to each other. So it's not just one transmitter and one receiver. You have the concept of a communicator and many listeners. Many of these listeners can become communicators, so it is duplex, really half duplex, and the communicator is called a talker and the receiver is called a listener. So you can have multiple talkers, multiple listeners on this protocol. The slowest active device on this protocol defines the bus speed, and the maximum allowed is 1 megabits per second. Up to 15 devices can be connected, again defined by the hardware protocol, and the maximum cable length that you can connect all these devices on is 20 meters. So you cannot connect between two devices, cannot have more than 2 meters distance. It is a parallel bus. So the RS-232 was a serial bus. In this case, it is a parallel bus, and of course the pinout diagrams are defined. So in this video, we really spoke about communication protocols, the hardware and the software part of it. We spoke about the meaning of these protocols, what they should really define, and we gave you an example of a serial protocol, the RS-232, and a parallel protocol, the general purpose interface bus, the GPIB. In our next video, we're going to be talking about a special device that helps you to do all of this more easily, that interfaces to the 8086. It's called the 8251 user synchronous asynchronous receiver transmitter device, USART. Till then, I would urge you to read more about communication protocols, especially digital communication protocols. The complexity is much more than one would assume. Thank you.